So welcome everyone to our first TMLS workshop of 2020. Yaron Haviv is with us. He will be our facilitator for today. Thank you, Yaron, for joining.
Okay, so thanks everyone. I'm Yaron. I'm co-founder and CTO for Iguazio, which is sort of a data science company focused on MLOps. I also host a bi-weekly webinar with sort of guest stars from the community, and I blog a lot. You can find me towards data science, writing about all sorts of things. So what we're going to do, we're going to discuss what is MLOps, what are the challenges that it's going to solve, and we're going to demonstrate an approach that we've been sort of talking around using a concept of sort of serverless machine learning with sort of a practice on how to do it, so you guys can see that it's for real and it's easy. And so we'll break it to sort of the first part will be sort of an introduction, presentation. Second part will be sort of slightly more hands-on. I will follow everything I'm asking you to do on my laptop. So if someone doesn't feel like doing it right now, that's okay, and you could go to it later. You can look into that URL that I'm just presenting now. It's my Git repository. So going to GitHub /Yaron HA/workshop, and you'll see that there is a page. I suggest to look at it right now because it does require to download few Docker images, and some of them may take slightly more time. So you can do it while I'm talking. Just do like, there's essentially 3 different packages that I'm going to show, and they're sort of built in a way that, with some configuration, they're very integrated. They'll work together, and you'll see how they're working. So there's like a Nuclio, which is sort of a serverless processing engine. There's Jupyter, any of you knows, but it's sort of a special build with all the examples that I'm going to show, which are already like baked in. So you don't need to do anything, just follow the notebooks that are baked into the container. And there's also like MLRun user interface for like experiment tracking and things like that built into it. So once you download those, then there is a sort of a set of instructions that you need to run in like a console. If you're a Windows user, then this thing probably won't work. So you just need to change this to like a directory, C/ something, where you want to throw all your data and artifacts into. So, but for Mac and Linux, this should work. And once you've run all of those, then you'll get like 3 different UIs, essentially the Jupyter UI, the Nuclio UI, and the like MLRun UI. So this is just go to that link, and I suggest to start. Anyone that wants to participate in the hands-on, just start downloading those Docker images. If you want, you can also play around with this to save time. So without going back into the presentation, I can, by the way, let me put the link in the chat. Okay, so I put the link in the chat, so anyone who doesn't want to type can use that. I hope everyone hears me okay, but let's start with what sort of is MLOps and what's sort of the driving factor behind it. So the general challenge is that we see more and more organizations that are trying to operationalize machine learning and AI and put it in the context of a business application. AI and machine learning is not new, but most organizations, the way they use it is more offline. You create a model, you create reports, you show the reports to the boss, everyone is happy, but it doesn't impact the business directly. But if you're familiar with like Facebook, Google, Spotify, Netflix, all of those, they essentially embed machine learning and AI as part of their business pipelines, as part of their recommendation engines or fraud analysis, etc. And that's more challenging. So what it means is that whatever you've done in the research environment, which is taking some CSV files or extractions of data sets from operational databases, running some playground around Jupyter or some AutoML canned solutions and building models and creating reports out of them, it's not really production worthy. And Organizations that need to build a production pipeline usually move to the thing on the right, which is building more like production pipelines where you bring data from all sorts of sources, ETL, real-time streams, integration with external APIs. And then once you're processing that, you usually need to do the processing at scale. So traditional Jupyter will not work here. You need databases or Spark, or there are other Python frameworks like DAX, DASK, sorry, or VAX, or others. And once you've done that, you may also want to automate the process of generating a model, because model sometimes takes half an hour to build a model, or you may want to run hyperparameter training, or you may want to run AutoML and try out different algorithms. So this could actually take 4 hours. So you need automation around the machine learning training and validation and data preparation process. And finally, when you generate a model, this model needs to be always on, needs to scale, need to respond and serve low latency. So usually people build out all this effort from scratch. It's not the data scientists that build the production pipeline. It's another set of teams, of machine learning engineers, of data engineers, DevOps, software developers, front-end developers, etc. And that becomes very, very expensive and very resource intensive. Many organizations fail in that process because, again, they haven't anticipated the amount of work. And one of the major issues is also that there's a lot of rewrite. So someone may write some code in Python, which is not designed for production or scale or performance. And this means that someone else needs to go and take that piece of code and rewrite it into Spark and Scala or Java or C, or maybe a better implementation of the Python code. And that really hinders the progress of many organizations. So if we're looking into what the process that goes, this sort of illustrates the problem. Some people write those jumbo Jupyters. If you go to a Kaggle, you'll see a Jupyter notebook that does everything from data preparation and training and validation and so even trying the serving, all that in a huge notebook of multiple pages. You can't really run that thing in production. There are some companies that try to take the notebook and run it in sort of a container, but again, that doesn't scale. You need to try and break this monolith thing into individual steps of data acquisition, data preparation or feature analysis, training, validation, deployment of a model into an endpoint, and so on. So this is really where a lot of customers I meet sort of struggle with this transition. And this is also a team effort. It's not the ownership of a data scientist to do all of that. It's a team effort. Organizations where there is no team effort mostly fail. Where there is a sort of an attitude of throw over the wall. The data scientist throws his notebook into someone else from a different team and waits for him to re-implement that. Those organizations waste too much energy and they don't succeed. Where I see more and more collaboration, where the data science team and data engineering and DevOps team all work in collaboration, this is really where companies manage to make progress. So that's on that front. So why is it so complicated? And this slide tries to emphasize the different things that we need to do in the transition from something that just works in my Jupyter or my PyCharm to something that runs in production. And those things actually get more and more complicated over time because we see more emphasis on auditing and liability, things like explainability, model monitoring. In order to increase model accuracy, people use ensembles and other more complicated graphs and combinations of machine learning. So managing that stuff in production becomes even worse. So what are those steps that we need to go through? The first thing, we take our Python code or some other code and we have to package it in a way that it can run in production, usually using containers. So we can take our code, build a container, add the required packages, the parameters, scripting around it. So that's the first step. Once we've done that, we need to think about scalability because again, running on a couple of megabytes of a CSV file on our notebook, that's nice, but working against operational database that generates like tons of rows and running against ETL, periodic ETL, and all that means that we need to think about scalability. Or if it's a serving function, I went to a customer, they worked like they had the model running 5 requests per second, and they had to deliver about 800 requests per second in production because this is the amount of traffic they're supposed to get. So one way is obviously, get 100 servers to do your workload, but just by optimizing, sometimes introducing GPUs, sometimes introducing caches, optimizing the code, you can increase sometimes by 1 or 2 orders of magnitude the performance. And that's probably much cheaper than buying 10 servers. 100 servers, sorry. When you go to production, you have to think about all those things that make it always run and make it sort of address the auditability and liability. We have to monitor everything all the time, like how much resources it's consuming, what's going on with our model, is it drifting or not. Even the data pipelines, we have to monitor things like lineage, how data transfers from one step to another. Explainability. How do we explain the model by tracking all the previous actions that happened before? How do we version? So if we need to go back in time, we can rerun the model and get the same results and not sort of get something totally different. And obviously, security is very critical, very important. Security comes in many forms. There's security for the access, for the APIs, the security for the data. How do we make sure that only the right people access the right data? Sometimes we need to anonymize data or encrypt data. We have access to different resources. We need secrets. So again, there's a lot of mess around security that needs to be addressed in production. And finally, we don't want things to be one-off. We want everything to happen automatically so we can increase our release cadence. Instead of building a project and after like 6 months, everyone is exhausted and now you need to do a change, no one has the energy. We want to build automated CI/CD pipelines, pretty much like software development, where you can just make a change, and that change will run through an automated workflow that adds all the missing ingredients and instrumentation and security and testing, and drive it into production with a rolling upgrade, essentially without taking the service down, without disrupting the service. So doing all of those things from my experience working with many organizations that are, again, not the top-notch tech firms, but sort of the medium average organization, takes more than 12 months to deploy all of that. Some of it is organizational challenges, some are technical challenges. I've even seen like 18 months for deployment, and it also requires, again, a multidisciplinary team, DevOps, data engineers, data scientists that need to work in collaboration. So essentially, what is MLOps and all of that? We're trying to automate this flow to minimize this work from months or a year to things that could be deployed within a matter of weeks. And that's done through a lot of automation. Okay. So again, what is DevOps? Trying to pick up on some term around here, is combining development and operations to shorten the system development lifecycle while delivering features, fixes, and updates frequently in close alignment with the business objectives. That's meaning that, yeah, we develop stuff, but really the impact that we want to make is on the bottom line of the business. If we're a financial firm, we want to reduce risk, we want to increase revenue, or an ethic company, we want to have more exposures, etc. So we need to use data science and software to improve the business objectives. And what is MLOps? Essentially a very similar definition. It has a lot of flavor around data science, which means that you have to think about this auditability and data lineage and experiment tracking and explainability and models and ensembles, all of those things that the traditional DevOps doesn't have. And that adds quite a bit of complexity. That's why it has its own term called MLOps versus just plain DevOps. Okay, so let's take an example of real deployment, real pipeline. Whether there's a demo, you could look at the link that implements this entire thing using sort of serverless features. But let's take a predictive maintenance pipeline. So the first thing we need to do is ingest data. And we may ingest data through some streaming data, sensor data being pushed through message queues, some operational databases that tell us information about the devices, the last maintenance, or whatever. We throw all this into sort of a data lake or historical data bucket. And then we need to start processing that data. And this data could keep on pouring because streaming keeps on pouring, operational databases keep on changing and updating. So we need to do that all the time. So once we've run processing, what is the processing is essentially building those more meaningful features through things like aggregations and groupings and joins and sort of all sorts of other data analytics techniques. And we form a base feature set, which is a denormalized table with lots of columns. Each one is sort of a feature. And we need to run this into training. But sometimes we have too many columns because we may have we may use even automation tools to generate features. So we may have 1,000 features. Running training on 1,000 features is quite intensive. So we may actually want to do a sort of feature detection, run some analysis on the features on sort of smaller scale, and choose those 20% that make 80% of the impact, and then run them through training. Usually in training, we'll split the data into a training set and a validation set, like 80, 20% or so. And then we run the training and the validation, and the training will generate the model. The validation essentially takes the training set and the model and essentially generates analysis and reports on the behavior of that model. So this is only part of our work. This is only the development pipeline, and you can see it's still relatively complicated. The challenge is when we're going into production. So the first step is obviously everyone talks about serving and creating a model serving endpoint with HTTP coming in, going out. Usually it's more challenging than that. You may have multiple models in an ensemble. Data may arrive in streaming and not in HTTP. But even when you do that, the serving has to have access to features, to real-time features. So what we have to also do is make sure that our ingestion layer and data analytics layer essentially writes into like a real-time database, like a NoSQL or a SQL database, where we can pull those feature vectors out of and serve the data. But again, we're not done yet. We have to also be able to track the entire behavior of our model. So we have to, everything that goes on in our serving APIs or serving model have to be pushed into, for example, a message queue or a stream. And that stream is being analyzed by another model that essentially looks at the features that are generated in production, looks at the features that were generated in training, looking, for example, into drift between those different data sets. Let's assume the average balance for most people is, I don't know, $2,000 in training, but then in production we see that it's $1,000. So that obviously means that our model will not be accurate, or if people click X amount of clicks per second, and then in reality it's a different value, that means that our model will now drift and behave differently than how we trained it for. So we have to run essentially tools that monitor all the data that's going in and out from the serving functions, run various other machine learning models on top of it, write the results into sort of logs and time series databases, etc. We may also, after we get labeled data, we have the actual results where our prediction is correct, etc. We run an additional analysis, essentially comparing the results from the serving with the actual results of the labeled data and figuring out, okay, our model is not accurate anymore. And that means that we need to go back into the upper pipeline and essentially run it again. And we have to do retraining. By the way, we may not want to do retraining on everything. So sometimes people build two models, one which is long-term model and another one which is a short-term model, and creating an ensemble out of the two. So again, they don't have to build a model out of the entire data set, and that will take hours. And lots of, it's not just a matter of time, it's also a matter of how many computation resources you're paying for. This is really expensive running training at scale on lots of data, especially if you're using deep learning and GPUs. So that's on that front. And some people may look like that when they finish building that, and we're trying to see how to avoid that. One of the key things in trying to avoid it is creating one ecosystem. Because right now, yes, you can go and take Hadoop and take Kubernetes and take some cloud provider tools, etc. So, and just the integration and the glue across all of those different components will take a lot of energy from your team and DevOps. So instead, trying to build an ecosystem that sort of connects to each other, tools that talk to each other with as minimal glue as needed. And that's what we're going to demonstrate next. So what do we need for a solution? We essentially need three layers. One, we need a sort of a feature store. We need a data layer. It could be based on managed data services in the cloud, managed databases, or object store or file, with some sort of layer of management on top of it. People refer to it as a feature store. The next layer above would be sort of the computation, the ability to run those different computation tasks really quickly and easily, and maybe even reuse the same components across multiple projects without writing a single line of code, as we'll demonstrate. And on top of it, we need a layer of tracking and monitoring and orchestration, etc. So those are the three layers. Again, regardless of which technology you're going to use, you have to essentially establish those three layers. Uh, and by moving into this architecture, if just taking an example from one of the deployments that we have, there's a nice use case on that in financial services for real-time, sort of fraud prevention. This is their original architecture, very sort of batch-oriented, Hadoop-based, running ETL jobs, running some analysis on that ETL job, building feature vectors, doing batch prediction that generates a reports, which is about 40 minutes after the fact that all the money was stolen. So it's really more like fraud detection or fraud reporting. And by moving into more of a microservice-based architecture, essentially all the data keeps on moving, and through streaming, through change data capture, the actual transaction that happened in the database feed into a message queue. That goes into a real-time feature engineering combined with batch analysis, how, in order to build features that are both long-term and short-term, running model training on this sort of combined short-term, long-term data, and running inferencing in real time, which is eventually blocks the fraudulent account within 12 seconds. But beyond just making it significantly, 2-3 orders of magnitude faster, it also costs a lot less because everything is dynamically scaling, and the ability to modify our pipeline, change versions, do retraining is remarkable because everything is a microservice. You just update something, you click, and it gets automated deployment, and you're done. Versus sometimes like a 3-4 months version cadence of updating something in a more monolith approach. So how does it build as a stack? So again, we said we need 3 layers. So the first layer is data. Usually you need 2 forms of data. One which is more real-time, high-performance oriented for storing like caching data across computation steps, or like real-time serving for all sorts of structure analysis and maybe fast data movement. In addition, you have the big data, data warehouses, data lakes, file storage, object storage, etc. that is used for the bulk data, or usually historical data. On top of those 2 different data layers, the common practice today is to use Kubernetes, because Kubernetes is an elastic clustering technology. Run it anywhere, whether it's a managed service in the cloud, on premises, through a bunch of vendors. It knows how to manage the memory, the CPUs, the GPUs, the jobs, everything you need. On top of Kubernetes, it's also a very generic stack. So unlike Hadoop, for example, which is very specific to analytics jobs like Spark or Hive, Kubernetes runs essentially everything, including the things that used to run on Hadoop, like Spark and Presto and Hive, but also all the machine learning tasks, all the tools, all the DevOps tools, etc. So we need another layer with all those microservices, but we want to try and harness those microservices as managed services or managed functions, because we don't want to essentially every time we need to deploy. If any of you worked with Kubernetes, have to create containers and YAMLs and deploy that using scripting. You want sort of one click or one API call to form a service, run a job, and decommission that once it's done, as well as instrument all the aspects again of monitoring, logging, security, all those challenges that we discussed a minute ago. On top of that, it's not enough to have nice microservices. We have to build a management layer for building those machine learning pipelines and tracking their progress, tracking the experiments, building sort of feature store where we store all the curated data in sort of catalogs and use them for training and serving, and also the ability to build real-time pipelines relatively easy. And again, some of those pipelines become more and more complicated. Again, model monitoring, outlier detectors, ensembles, validators, all those things have to exist on a real-time pipeline as well. So it is, again, more complicated, and we need something as a source code or source control tool, usually like a Git repo, where we put everything, the metadata and the code for running our work. So a few words on sort of this serverless approach, why do we want to do it, and maybe after that we'll open some time for questions. So what is really this concept of serverless or microservices? So on traditional architecture, we had one big monolith, or even we talked about this Jupyter notebook that has everything all in once. And that means that first, it's really hard to refactor that into something that's working in production. We can troubleshoot. We may also want to scale each tier individually. Maybe just scale the training or just scale the data preparation. And each one of those steps may have a different tool which is best used for that. Maybe for data analytics, we can use Spark or Dask. And for training, we may use like Horvath or other frameworks for horizontally scalable training. So we want to break our pipeline into individual components. Breaking it to individual components also allows us to make reusable components. So, and we'll show that in the practice that essentially a training job is a training job. There's not a lot of news around that. So if we have a function that knows how to do training for XGBoost and it gets a data set or a data frame of input and essentially generates a bunch of nice reports and a model for the next step, we don't have to rewrite it. We can just implement it once. And if we need to add our own sort of secret sauces on our organization on how we want to monitor and log all the results, we can do it, but we do it once. Where usually things change is the data preparation side or building the feature vector side. And again, this is where you'll probably want to do more software development to address your unique business needs of joining and aggregating different data sets, forming this data panel that later on feeds into the actual machine learning pipeline, and other places also on the serving side, building the real-time feature vectors, integrating with the operational application that use the notifications coming from the machine learning, etc. So this is the general idea of breaking those monoliths to sort of microservices. And there is in general, in the industry, we see more and more trend towards those sort of function engines. So what is a function engine is, unlike a container, is essentially more managed. That you take a piece of code and you tell some machine to go and run it with all those requirements that we discussed: monitoring, logging, auto scaling, integration with other elements of the stack, etc. Where unlike container, where you build a container, you have to configure the container, you have to feed data into the container, you have to figure out how to do scaling out of that container, etc. So you've seen the first wave of serverless engines like Amazon Lambda and others, but we see more and more serverless engines geared now towards or managed services, which is also sort of a form of serverless functions geared towards data analytics and machine learning, etc. So this is another trend that we see. In Iguazu, we support two major open source projects that are active in that space. Nuclio is sort of the veteran, with about 3,500 stars in GitHub. It's more around real-time and event-driven workloads, things like serving, data analytics, stream processing, etc. And MLRun is more sort of end-to-end ML orchestration, which has also batch-oriented serverless functions for like training and data analytics and other things. And the general idea with those engines is the first, they automate all this process of turning your code into a production microservice. Production microservice is not only the container, it's also the integration with files and databases and objects, the logging, the monitoring, the telemetry, the security, execution roles. Lots of hassle that is usually done by your DevOps team can now essentially be automated. There's a great use case that's public by, for example, network appliance, using in their predictive maintenance pipeline, how they essentially move their predictive maintenance pipeline to a serverless technology and cut 90% of the amount of code and DevOps work. Not to mention time to market and cost, because usually serverless is elastic and you pay just for what you're using. So they cut about 80% of the cost, 90% of the amount of code and DevOps just by making this transition. Usually serverless is slower, but those engines that we're talking about are much faster because they're using some real-time high-performance processing engines underneath. So they know actually how to make your code run faster, not slower. And as we mentioned before, by creating those microservices that are serverless components, we can create a marketplace and store all those functions in sort of a general repository. This gives us a few benefits. First, we want to build a pipeline. We drag and drop a bunch of functions and we create a pipeline. Some of those functions, again, are repetitive, like a training job or like a notification to Slack or whatever. So we don't have to write them again and again. The second is because it's a version repository, that means that we can now collaborate. So maybe a data scientist writes a piece of code and a data engineer takes that code, improves the exception handling, improve the data access, and creates a new tag on that function. And this tag can go into production. So if you maintain the external APIs for that function the same, you can just go and improve it over and over, and just create new versions of that. And with a single click, you do rolling upgrade, and it's going into production. And the last feature, which is very unique, is the ability to scale out beyond just the traditional serverless scaling, which is done using load balancing. There are techniques for machine learning that are slightly different for scaling. You need to, for example, scale out your data frame, and there are technologies like Dask or Spark RDDs for doing that. You need to scale your training, and there are technologies like MPI and Horvath, if any of you heard of that. Used for that. So part of the work on the MLRun, for example, serverless function was to build integration with horizontal scalable engines like MPI or Dask or Spark or others, and put it on a very high-speed data plane that allows us to horizontally scale very demanding jobs. So if you need to train on a very large data set, you don't have to essentially buy a huge virtual machine. You can essentially horizontally scale your workload across machines with GPUs and CPUs. And so those are some of the unique attributes of this serverless technology, which again is all open source. Maybe one, just again to highlight what's the difference between some of those serverless technologies and the traditional serverless approach is that usually things like Amazon Lambda, it's a very short-lived. The way they scale data is using load balancing techniques, scale processing, usually stateless. So if you want to process lots of data, there's a challenge, and they're usually, again, driven from an event like a JSON structure or a HTTP call. Where in data science, we want it slightly different. We may have jobs that runs for hours. The way for us to scale the jobs is using things like hyperparameter tuning or shuffling or data partitioning. Usually it's stateful because we are processing data after all. And the way that we want to pass data from one function to another is not through a JSON event. Sometimes we need to pass a terabyte worth of data set. So you don't really want to push it all into a JSON file. So again, that's the general idea. And this is what led us, together with help from other industry members, to push this concept of managed executions, which buys you another key advantage. So one of the things that everyone wants to have is explainability, is ability to run something and record everything that goes in, everything that goes out. And by creating those managed runtimes, you essentially think of it, you have this sandbox, this orange sandbox, that everything that goes into that managed execution is automatically recorded. Every result that goes out of that managed execution is automatically recorded. And there's also a way to pass things like secrets and security credentials in a very safe way into that sandbox. So you can run against like operational databases without, or you don't have to put passwords in your Jupyter notebooks. And that also ties into seamlessly into pipeline processing architectures for both real-time and batch architectures. So this is the general idea. I mentioned Kubeflow. Kubeflow is one of those tools for managed machine learning pipelines, very similar to Luigi or his name escapes me, another tool used in Hadoop ecosystem. And this allows you to essentially take multiple steps. The traditional way that Kubeflow works is that you have to orchestrate containers and lots of YAMLs in order to make it happen. By integrating it with the serverless functions of MLRun and Nuclio, essentially every step in the pipeline is a function step, as we'll see in a minute. So I can build those functions separately, and the only thing I need to do is take a canvas or take an API and build my pipeline and tell it go and execute that pipeline. Okay, any questions until now? Maybe we'll open it so you're not swamped with too much material. Any questions whatsoever? There is one question here around the difference between online and offline feature store. Are they expected to store operate with different expectations? Yes, obviously. If we'll have some time, I may demo sort of this is an incubation technology, the part of the MLRun of real-time online and offline feature store. And the general idea is that when you're doing training, then usually it's a batch process. Usually feature stores are broken to what is referred to as a feature set, which is how you collect data and put it into sort of, think of it, a set of tables. Those tables will usually reside in at least two implementation. One is a real-time one in like a key value a database or a SQL database. The second one is more of a batch in a data warehouse or like Parquet files. And when you're forming a feature vector in training, what you usually do is you'll do sort of a join or a time travel refers to sometime. If you know pandas, it's called as of join, join as of a certain point in time. And this builds your training set. And that could take 15 minutes or more to build, because there is, in a feature store, it's not just the store, it's also sort of an analytics pipeline. Again, if I'll have a few minutes, I'll show you how it works. And when you're in the real time, you have a model serving function, which essentially does a get operation with, for example, a user ID, and expects the feature vector to come in sort of a few milliseconds. So there's a very different architecture of obtaining those two. One usually using like stream processing and key value stores for the real time, and for the offline is usually like data lakes, Parquet files, batch processing. Luckily, because we have in the same framework, we have the real-time engines like Nuclio, and we have the batch engines like MLRun, and we can orchestrate those two pipelines seamlessly. And if I have time, I'll demonstrate that. It's still not a GA functionality, but it's pretty cool the way it works. So I see the question, a few other questions there. Where TensorFlow extended fit into, I think TensorFlow extended is again very limited to TensorFlow, and we'll show how we want to extend all those things of model servings to machine learning pipelines, of all the data preparation and others too, across all the different components, whether it's XGBoost or scikit-learn or PyTorch, etc. So we're personally not big users of TensorFlow extended, and we've leveraged other open source projects that have the same functionality. Other technologies besides Kubernetes, what are the downsides of horizontal scaling? Okay, so again, there are many technologies, and Kubernetes is more of the infrastructure layer. On top of it, you have other layers like Kubeflow, which is, I have a blog on that recently from last week in Towards Data Science. You can read, and actually it also covers the different components that you need in a stack. Obviously, we recommend the open source project that we're working with, like MLRun and Nuclio. Dask is very handy when it comes to people that want Python native approach to horizontal scaling of machine learning and analytics, similar to Spark in some cases, but very Pythonic by nature. So we've seen organizations that move from Spark to Dask, although it's not the same maturity, really become much more agile, because the data scientists work on the same architecture for scaling out and for playing with their notebooks. Other questions where is Kubeflow framework agnostic? So Kubeflow by its nature is Kubernetes oriented. It was actually developed by Google, the same team that developed Kubernetes. So it's very Kubernetes oriented, but the idea is that it resides on top of Kubernetes. That means that you can have it everywhere: Azure, Google, Amazon, on premises, etc. And again, you can refer to my Towards Data Science blog post on that, on sort of its advantages and disadvantages, and where you need to recording. Yes, I'm sure we'll have recording around horizontal scaling. We've seen people cut costs by 80% by moving to dynamic horizontal scaling, because what you see in many cases, people allocate virtual machines, and they just, they go to lunch, the virtual machine is still allocated. They run a job, the job doesn't scale to fit into that VM, or they may spend too much money. So by average, from use cases I've seen, it's about 80% cost reduction if you work against a cluster of containers and just allocating containers as you go. So if you have multiple data scientists that work on the same cluster, let's say one runs a job finishes, all the containers, all the resources are decommissioned, someone else runs the job. So that means that you can use a much smaller resource pool and get everyone much happier, because when they run something, it will run 4 or 5 times faster. But on an average cost, you will save about 80%. There are even ways to do it more efficient. We've done more and more integrations with the Spot instances in the cloud, which are essentially cheaper VMs, because you can essentially allocate dynamically resources. You don't really care that the Spot instances essentially just evaporate. So you can use something which is much cheaper, and again, reduce the cost even further. Okay, so with those set of questions, let's pause here and move a little forward and let you guys do something in addition to me talking. Okay, so what is this approach of serverless development, or sort of faster, rapid development to production? So everyone really likes to work with their own IDE. Okay, people want to use their Jupyter, they want to use PyCharm, maybe, or VS Code, because they want to put breakpoints and debug thing easily. But still, you need to track everything that happens even in development, not just in production. So one of the things that we've done is, okay, you just import an SDK, and we'll practice that. And that SDK will automatically record everything that you're doing in your native development environment, including the experiment tracking, the lineage, all things that we discussed. At a certain point, you want to run the same thing that runs on your Jupyter or PyCharm. You want to run it on a bigger cluster with access to lots more data, or maybe horizontally scale your workloads. So that means that now you have all this hassle that we discussed before, which is turning it into containers and instrumentation and YAML files and all that sort of fun. Instead, I'll show you essentially write a single line of code or a single CLI command using the MLRun SDK, and it essentially knows how to package your code with dependencies, throw it off into the remote cloud or your local Kubernetes cluster, build the containers for you automatically based on the manifest, build the resources on Kubernetes for running the job, tracking everything, essentially back into the database where you can see the experiment tracking, just like it was running on your notebook. It actually even responds with your console all the way to your client ID, so you have the cozy feeling that it's actually running on your notebook or on your ID. So this allows you to essentially, with a single click of a button or a single command, run the same workload that you had on your laptop in a sort of much bigger cluster with more production capabilities. You're done, you essentially just go and store everything in a Git repositories. And by the way, when you generate the jobs and the functions, you'll see that essentially you're also immediately cataloging them, so you can later on use them for other things. As you go closer to production, a single function is not enough. Maybe you've worked on a training function or a validation function, and now you need a data preparation function or a model serving function or an outlier detection function. So the general idea is to build those functions and then take those individual functions and combine them into a pipeline that has all multiple steps. It could be a batch pipeline or a real-time pipeline. So, and if we're really, really advanced, you can even implement that as part of a CI process. So every time someone takes and builds a new function, there's an automation, and I'll show you one example of that takes all those different functions, builds the entire pipeline, runs the entire pipeline, tracks the results of the pipeline, respond back into the Git pull request or even a Slack notification, etc. So everything is fully automated when you're running those machine learning pipelines. So that's the general flow that we're going to play around with. Okay, and it's not just the training and all of that. There's a significant amount of effort in what we call the post-production. So we have the serving engines running, taking the models from training. But then we have to track those in real time to identify concept drift and also accuracy misses. And at a certain point, we want to have graphs and charts like the ones that you have here, which is an implementation in Grafana of the model monitoring capability. And then if you see certain things, you may want to trigger a retraining or a rebalancing of your ensemble or things like that. So there's a lot of machine learning. It's actually harder machine learning in the production side, not just in the model development side. Okay. So let's move into the practice and demo. Hopefully, you guys already downloaded the different packages that I mentioned. Anyone has challenges with that until now? Did everyone manage to do Docker polls, and do people just want to avoid it and want to continue presentation? You guys, you can be vocal. You can say whatever you think. Okay. I assume everything is okay. So essentially, what you need to do is run again those different commands. So again, create some network for our microservices to work, run the Jupyter with the pre-baked stuff, and the MLRun user interface, and the Nuclio serving engine, processing engines. MLRun supports a lot more processing engines like Kubernetes jobs and Spark and Dask, etc. Just harder usually to deploy some of those. So this is why we're focused on just on this part. If you want to go into a more advanced deployments, if you go into the MLRun repo and you go into the read the docs, you'll see how to install more complicated configuration with Kubernetes and shared NFS for files and things like that. But for now, let's stick to something relatively simple, which is only using Dockers. So once I've run all of those, I'm using Windows and it works for me. Then we're going to have three different services that we can access through local HTTP. So we have the Jupyter Lab, we have the sort of Nuclio UI, which is the serverless function engine. We have MLRun, which is again more the orchestration and monitoring of all those jobs. So let's go now to the Jupyter notebook, and let's look at a few simple examples. So this is an example of a really trivial function, which does some sentiment analysis using a text blob Python package. So it looks like a regular notebook at a certain point, but it has a few extra things. So first, we need to import the Nuclio SDK. We put some ignore here, which means don't use this line in when you're generating the container. So ignore it in compilation. Then we have a set of magic commands. Magic commands is essentially I can put some commands that don't impact my processing. Actually depends on the flags I put here, because here I'm installing this package, and it will also install it in my notebook, but in the same time it will record it into the function manifest. When it's going to build the container, the Docker container for the function, it's actually going to look into those things, the pip install and some configuration. There are many other configuration details, and you can just like Kafka triggers and cron timeouts and like number of GPUs that you need, etc. But I won't dive into all of those. So again, we're just putting some magic commands to define our dependencies. And then I have again a relatively simple function. This function is essentially taking some text, some language, and based on it's doing text correction, it's doing sentiment analysis, subjectivity, and responding with the translated data. It's also using sort of prints and logs into that thing. So when I wrote this function, I also need to wrap it in serverless engines. You usually have a handler, something that gets invoked every time there is a message, like an HTTP request or a streaming message or a job start. So I have essentially a handler wrapper that wraps my NLP function and takes the body from the request that is coming and throws it into my NLP function. And there's another marker here. You see end code, essentially telling the compiler that I'm going to use in a second that my code essentially ends here. From here on, it's sort of more testing and other things. So as I do that, the next thing I can do is just, let's restart the notebook. Okay. So here it's also installing the dependency locally. You guys can just follow what I'm doing right now. Just one comment, usually in Jupyter, you need to restart after you're installing some packages. So you may want to do that, restart again. And now I'm taking my function code, taking my handler, and now let's run my function code. So you see I have a function, and it translated my good morning to Spanish, or let's do it in French. Okay, and I get the sentiment analysis. Again, relatively simple function. Now, let's assume that I want to make this function something that runs in production. So the only thing I need to do is tell it, take this notebook and make it production. I didn't tell it notebook, so there's a parameter here called file name. Okay, if you keep it blank, it knows it's the notebook. You can give it a file name of a different notebook or a Python file. It will pick it up as well. So I just created this function object, and then I'm just going to some it's down. Anyway, you guys should try it as well. I think it should work. This is the Nuclio UI, so I can see the same code that was running in my notebook should be teleported to here. There are a lot of other configurations that you can do around, setting CPUs and GPUs and memory. Those could be done from the UI or from the SDK, and it could work both ways. You can set things like triggers. HTTP is the common ones, but you may want to do things like Kafka or Kinesis or others. Those will become triggers to those functions that we're using. Okay. Okay, I'm not sure why it failed on me. Let's see if any of you have an issue. Maybe something went down on my microservice. There is a question, can Nuclio be deployed on AWS? Yes. So Nuclio can be deployed on any cloud. There's actually a lot of, there's also tutorial, I think in Katacoda. First, there's like Nuclio. There's Nuclio.io site with slightly more references and documentation. And if you search like Katacoda and Nuclio, there's actually you'll find like online tutorials of how to go and install Nuclio. Again, it's very popular and used by a bunch of large companies, including like Samsung, Apple, and others. I think it's this one. So you can have like a tutorial of how to install it. If you're using Kubernetes, it's just like one Helm chart that you can install, and it just works. In Docker, as you've seen, it's relatively simple. You just go and install with the single Docker run command. So anyway, this is the part on the Nuclio. I'll try and debug it in parallel. There is a question: is Nuclio better than SageMaker? Nuclio and SageMaker are relatively different. You can actually use Nuclio from SageMaker. Again, very easily. SageMaker have containers. They're not really serverless. You can't really use Lambda functions for serving because they don't have like GPU support and sort of other like stateful things, etc. So you can actually use deploy the SageMaker models using Nuclio into production. There's another interesting question: how does Nuclio differ from Kubeflow? If you go into Kubeflow and look into some of the components, you'll actually find Nuclio as one of the official Kubeflow components. Nuclio is different than there is in Kubeflow. There's another project called KF Serving, which is slightly different. The Nuclio is a serverless engine. It's a fully managed execution. You write a piece of code and deploy it. If you use KF Serving, you need to create the Docker container. You need to create the YAML files. You need to manage the execution and all of that. So again, if you want to work hard, it's okay. The other point is that Nuclio, because of the real-time processing engine, is significantly faster than KF serving, and you could ask people to try that. So how is it to debug Nuclio if it's not a container? So usually what people do is they debug it using the SDK in PyCharm or something like that, and then they do deploy. Just like I've shown you here, and I'll show it in another demo in a second for the model serving. So there is what we call mock server, there's a simulator, and you can work against the simulator. And once it's ready, you just go in and deploy it, and it has logs and debugs and all of that built in. Again, those things you will probably not find in things like KF serving or the other frameworks. And if you're really lazy, then Iguazu has a managed service where you don't need to install any of that, and we bring you sort of something fully working and managed. So that's on the serverless part of just showing you how I can take a concept of a function and turn it into something that works. You see, I'm working on my own laptop. I don't work against the cloud. It just and I can play around with it. Let's look at another more batch-oriented scenario. So let's assume I want to run some feature analysis. Let's take a simple example that we've seen before. I want to do some feature analysis, training, and then validation of a model. So essentially what I want to do is I want to leverage the function marketplace. What is the function marketplace? It's essentially, there is a Git repo in MLRun of a lot of different pre-baked functions, fully documented, that address many different scenarios: real-time, offline, feature engineering, embedding, NLP, deep learning, etc. And those could be accessed, like I'm going to use the describe function, which is a feature analysis function. Every one of those functions have full examples, documentation, etc. But I'm going to use them in my pipeline. I'm going to use few of those functions in order to run my jobs. And I can take those functions and I could also build them locally and store them locally, or store them in a Git repository. So again, let's take this example. So we're going to import the describe function of feature analysis. We don't really know how it's used, so let's call the documentation. It has the notion of auto documentation from your Python code. And I can see what are the parameters that I can use. So in this case, I'm going to run this function. I'm going to use something called run local, because I don't want it to run in the cluster, because I don't really have full Kubernetes here. And so I'm going to run it locally, which is going to sandbox my code. Remember that I said that all the inputs, all the outputs are going to be auto-recorded. So by doing this run local operation, then I can essentially take this describe function, push specific parameters and specific inputs. Inputs is data objects, where parameters are sort of more like simple things. Data objects, the reason that we separate parameters from data objects, because data objects go through auto lineage, and they go through also, like, if this is an example for something in S3, when my function gets executed, it's actually going to get a local file access. So it also downloads the file for the execution. It uploads it on the sort of the way back. So and you can work with schemas. There's a notion you could say like S3, or for Azure file system you do like AZ, or for NFS. There's again all sorts of notions that we sort of schemas that we support for special storage types. And there are other many cool things around the inputs, but I won't go through all of them here. So again, I want to do a feature analysis, say what is my label column, what is the data set, essentially the traditional iris data set, and just want to execute it. In a minute, I'll show you how I'm doing exactly the same, just going to execute in the cloud. And then because it's sandboxing my code, I can see all the progress of my execution, my logs, my labels, all the parameters, all the outputs that were generated out of that thing. If I want to go into the UI, I will see exactly the same because everything goes into a database. So I think it's not this project. Okay, so I had, for example, the describe function. And when I go into, by the way, there's every version that runs is recorded, and I can scroll through the versions into historical data. I can actually see the code that I was using. I can see all the parameters, which machine it was running on, which workflow pipeline, etc. I can see all the inputs and all the outputs that were generated by that function. They're all recorded in the artifact storage and the dataset storage, and I can just see all of them. I can see the results, if there are any, the logs, there are no logs, etc. I can also see it in a different view. I'll show you that in a minute. I can also see, model management and data and structured data sets and others. Again, even the code is recorded. I can go and see the code that was used. Oh, not in this case, sorry. It's probably temporary file. But if it's a package file, if it's running as part of a distributed cluster, then you can actually see the actual code that was used and the hash of the code, etc. Okay, so that's, again, running something relatively simple. In the demo, it's actually going to land in the /data/plots. So I can just go here, data, plots, and you could see those charts that we've seen in the UI. Again, part of a managed cluster or a Kubernetes, it flows much simpler because it's using like NFS or object store as a file share. Yeah, and you ask, like, can I specify GPUs? Yes, you can specify as part of the function object, you can add GPUs or define the scaling level, how many nodes they're going to be used. Some runtimes like Dask support different tolerance. You can say number of nodes between 2 to 5. It will auto scale between those two. Same for Nuclio runtimes. Okay, so again, I did the analysis and I generated all those nice feature analysis capabilities. So now I know all my features, their statistical behavior, etc. The next thing I want to do is, well, I can take the same job and run it on the cluster. It will just look a little slightly different. Again, I do need to use some sort of distributed data like NFS or object in that case. So here I would mount, in this case, mount an NFS, but you can mount object and other things into the function. You can also specify here GPUs and scale and a lot of other parameters, memory limitations, again, to the function object. Now let's run the training. So I want to use the scikit-learn classifier, which is like an AutoML classification engine. It accepts different algorithms for the training. And essentially, I'm giving it some parameters like the column label, the size of the testing, the type of the algorithms I want to run, and the input data set. And it will generate all those different results from the training and all those artifacts. So we have more artifacts here, the confusion matrix and others. And again, all the results, I don't have to look here. I can just go into the database and see them. I can just see them here, the training. Okay, I can see the results of my training. I can see the artifacts that were generated by the training job, etc. And you see here that I actually didn't really need to write any training code because it's so standard, running training in scikit-learn. And if you want to see how the implementation looks like, you just go to the functions hub and it's all, again, open source. So that's on that front. So we created training. Now, the result of every run is an object. It's actually an object that I can query. So for example, the training run.outputs is the result that were generated by this thing. You can see some special URLs like this one. This is essentially saying it's stored in the feature store or the model store. So it's also version. You see a hashtag and versioning. So again, it's all done automatically. And now I want to run validation. So the nice thing about those result objects is that I can refer to them. So I can run the validation on the output of my training. I can take the model that was done in the training and use it as the model in the validation. To take the test set from the training, use it for the validation, and just generate another set of charts that show me all my validation. So now what I've done is everything is running on my notebook. So it's not really too sophisticated, but it is very helpful. You see, everything is being tracked. In a minute, I'll show how I'm running all this in a distributed cluster. Okay, and again, we can go into the system and look into the test classifier. This is all the results from the testing. Okay, if we go into the artifacts, we can see that actually the artifacts are structured. So if I have a table artifact, I will see a preview of the data. I will see the metadata statistics of the data that was generated. If I'm going into a model artifact, again, there's lots of data, also auto lineage, as we mentioned. We know exactly what was generating that. We know for every artifact which execution was generating that with hyperlinks. We can even view all those. It's like slightly more sophisticated model. Anyway, again, there's different types of artifacts that are generated, and each one has some more specific metadata. And so going now into the third example here. Let's assume we want to build. This is really going to show the differences of like the other serving models, model serving functions, and what MLRun serving does, which is essentially another higher level abstraction on top of Nuclio and MLRun. So let's assume I want to build a serving engine. My serving engine may actually support different types of models, maybe ensembles, maybe even a full-blown graph with multiple steps, like validation or outlier detection, etc. So I can just, again, the same tricks, import MLRun. It also imports Nuclio, so I didn't have to import Nuclio. I'm just telling it now that it's a different processing engine called serving, which is essentially stands for the MLRun serving or the special flavor. There are other kinds like Dask, Spark, and others. And the typical kind will be job, which is like a Kubernetes job for batch. I can give it what is the baseline image that is going to be used by that, and potentially I can install a bunch of additional packages. Now here, when I'm doing my serving, I don't need to implement a full-blown serving function. The serving engine works with serving classes. So you give it a class, which inherits from a serving class. This parent class addresses all operationalization stuff automatically for you, including like model drift analysis and routing and lots of other cool goodies. The only thing that you need to do is just implement two functions. There are also other hooks that you can implement, like explainability and others, but we'll keep it simple. And it's fully documented. If you go into to MLRun and go under the serving, there's examples for that. But if you go into serving, you can see a full example of how you build models and how you create serving functions, how you build like routing rules, monitoring rules, etc. built into that. But again, going back into our notebook, so I created a classifier class, which essentially loads the model. It's using some method internal to the class for loading the model. Again, knows how to do a lot of interesting things while loading the model. Some models are actually spread across multiple files and have metadata and parameters. So when you get the model, it knows automatically how to also bring all the metadata and multiple files, etc., into that. You're loading the model, in this case, using the scikit-learn method. And then in prediction, I just wrote the body into like a classifier, and I return the results from my classifier. So 10 lines of code, I have a model serving function. And now let's take some model from the internet. Again, the iris model that was essentially generated by the previous pipeline. And now we want to create a function. In this case, when we're creating code to function, notice that I'm also adding labels and sort of categories. I'm pushing it into the marketplace. So next time I may want to use the function, I can search through that. If I go into, for example, jobs, I can create a job, and I could choose from one of those functions that I'm using, and then I can create a job from. I'm not sure it's not working here. I'll show you that in a minute in the Kubernetes cluster. And there's a configuration issue here. So anyway, the idea is that once when I'm tagging and doing that, I can actually go and create a job. I can store it, and then I can just go to the UI and launch a job without even going back into my notebook. So I create a function out of my model class. The next thing I'm doing, I'm adding a model. The model is essentially this file, this pickle file here. I can put a lot more parameters when I'm adding a model. And I could add multiple models to the same function. And I can even add things called routers, like ensembles and other things. We'll keep it simple for now, single model on a function. And what I want to create is once I created a function which has code, it supports a model here. And then I want to create a simulator that allows me to go and test that code of mine. So I'm taking the function, I'm creating sort of a simulator, a mock server, which essentially simulates my real-time function. So now I'm just taking and creating a data set, simple data set from the iris data set. And I'm testing my function. I'm giving it like the actual URL. It does follow, by the way, the API follows the model serving protocol of KF serving v2 and Triton, NVIDIA Triton, if anyone of you used it. So it's a standard serving protocol. It's not like something we've invented. We just make it faster and simpler to use. So I can essentially test, give it like v2 models, name of the model, an operation like infer, you can do explain, you can do other things, and give it a data set. I don't want to return the entire data because it's large, so I'll just show you that essentially what I got is a structure with the ID, the model name, and the output vector from that. Now, in order to deploy this function to a real microservice, I just need to say deploy, point it to the cluster I want to deploy at, which is also nice because I can develop in one place and deploy in multiple other places. We're actually going to demonstrate, like I think a week or two from now, a joint solution with SageMaker, where from SageMaker we can actually deploy in multiple edge locations with a single operation. So again, I can just go and deploy. Those functions will later on appear on the on the Nuclio. On the Nuclio front, I'll actually see that function that I showed you a minute ago. It's actually running. I can see the code. I can see all the configuration. I can change the configuration. I can test my function. And I didn't put it there. I just said deploy, and the deploy knows how to pack my code and throw it into the system. So there is a question here about asynchronous request support. Yes, supports a lot of asynchronous. Again, Nuclio is a parallel processing engine. By the way, it supports up to 400,000 events per second on a single process. And obviously, to achieve such performance, you need asynchronous processing, like not blocking performance. And you can also, one of the things about asynchronous processing, you don't necessarily want to use HTTP. So you want to use something like Kafka or Rabbit. So this is where you will create a Nuclio function. Just instead of HTTP, you can specify it either through the API or through the UI. You can just say, give me Kafka. When you do Kafka, it also automatically supports partitioning, rebalancing, etc. So again, very, very scalable and very efficient. So that's regarding asynchronous processing. So again, I deploy the function. The next thing I want to do is, again, take some test data and run it against the real endpoint. So when unlike test, invoke is actually working against the real endpoint, and you see that it responds with the same thing. So essentially what I did here, in a relatively simple notebook, I developed a model serving class. I tested it, I cataloged it, stored it in a function repository. I used it, added some models. Again, simplistic thing, but you can do more sophisticated serving graphs. Deployed it, again, tested it, and deployed it and tested it in production. All that in a single notebook that any one of you can do. Just think about what is the alternative. The alternative, you write some code, someone takes that code, generate containers, generate YAML files. If you think about integrating something like Kafka, who handles all the checkpoints, rebalancing, high availability? Everything that happens within the function goes into monitoring, goes into telemetry, into Grafana. There's auto tracking, everything that goes in the function, it immediately goes out into a stream where there is a drift detection analysis on top of that stream. So all those things you didn't need to do. The only thing you need to do is just say deploy and test, and you publish it, you put it in a repo. The ML engineers or DevOps guys will just pull it in and use it in a production pipeline. So with that, let's do some more production pipeline now on a bigger scale. So I have another notebook which is coming from the demos repos. So again, MLRun has lots of demos of like full-blown pipelines. Let me open my. Okay, here it is. Sorry. So if you go into to MLRun repo, there's like demos repo where you'll see all sorts of examples of like deep learning and machine learning and churn prediction and predictive maintenance, etc. And one of the simplest demos there is what we call the scikit-learn demo that shows a fully automated machine learning pipeline, which combines MLRun and Kubeflow and Nuclio and all those different tools under a single demo. So you can just download that demo from the MLRun/demos. But let's look at that notebook. So this notebook, what it shows me, hide my credentials. Sorry. What I'm doing here, I'm taking the same local notebook that I have. Just I don't want to install on my laptop a Kubernetes cluster, so I'm just accessing our managed service. But again, it could access your Kubernetes cluster just as well. You just need to set a bunch of environment variables that tells it sort of the access keys and credentials for the remote cluster and the URL of the remote cluster. So once you've done that, now I can actually do exactly the same that I showed you before, just against a much larger and fully automated cluster. So again, here I'm building a new function which is just about data preparation. It takes the iris code and builds it and logs it as a data set into the MLRun, the artifact database. It also uses logging and things like that. Again, it's a microservice. We want to be able to monitor all the different aspects of the execution. And the other thing that we can build is a project. And the project is a container for all those different functions and experiments. Sometimes, again, you have the churn prediction project or the recommendation engine project. It allows you to break those into logical elements. And then I'm going to use the same thing here. I'm just going to take my function, my iris generator function. Just in this case, instead of running it locally, I'm running it on a remote Kubernetes cluster. And you could see that actually one of the things that's tells me here is a pod ID, which is the container ID that is actually running on in the cluster. But it is on my laptop. So it's essentially teleported the code into the cluster, created all the Kubernetes cluster resources using the MLRun remote service, runs it, responded back with all the logs and telemetry, and completed the job. In this case, the data itself is stored on our distributed file system, but you can also use something like S3 or Azure Blob Store or NFS as a way to share the data among the different containers in the pipeline. Okay, so I'm just running this analysis, but now let's see how I build a full-blown pipeline. So a full-blown pipeline, I need all those functions that we've seen before. I need the classifier, the tester that we've seen. I need the model server function that, again, this V2 model server function we just had. And I'm adding another component here, which is a model tester. Once I have a model, I want to run all sorts of real-time tests against the model to see the performance, evaluation, and behavior of our model as a production microservice, not just something that runs off my laptop. So I'm just importing those functions. And now I'm creating a pipeline. This is using the Kubeflow language. This is why, when you ask how does Nuclio compete with Kubeflow, no, it doesn't. It's essentially Kubeflow is one of the Nuclio is one of the components in the Kubeflow ecosystem, and actually you can build a machine learning pipeline where every step in the pipeline will be a function. And what my pipeline does essentially doesn't do any coding. The pipeline just defines the wire up, how one function connects to another function in the pipeline, like which inputs goes into which outputs, etc. So you can see I have my ingestion function. I can even have CI function. This is like a function that builds a container, and another function that does data engineering. I give it a name. I'm telling it to use the image from the build, giving it some parameters, and dump the data in a certain place. So, and then I'm taking the feature analysis function. I'm telling it, go take the data from ingestion. Again, exactly the same language that I used locally before in my previous notebook. Remember, .output of types, name of artifact. So I can actually play around with my notebook, and we have users that essentially work in their on-prem PyCharm. They flip a flag and run against a cluster. Go back into their PyCharm, put some breakpoints. Now flip a flag, and they're running against a large cluster. There's also a way to work with remote PyCharm and remote VS Code, by the way, and run their kernels on the cluster itself. So again, we have the analysis, we have the training. In this case, we're leveraging MLRun hyperparam and AutoML capabilities, so it knows how to run a series of tests, not only one. So here I'm essentially running 3 different algorithms and asking it to select the one with the best accuracy. And again, I'm building this entire graph, saving it and just executing the graph. And after a while, it's essentially going to respond with the entire pipeline results. In my notebook that is on my laptop, I didn't even log into the cluster. Now, let's assume we want to log into the cluster. So this thing that I just showed you, this is our managed service, but again, you can do it yourself, is using Kubeflow, where I can see for every step in the pipeline, I can see the different results that were generated by this pipeline step. Remember, I had this sort of CI step and the data engineering step and training. And then I did testing as well as deploying the model into a real-time microservice. And finally, I ran the model testing, which is measuring the latency of my model serving function as a production microservice. So this entire pipeline, I just did off my laptop with 20 lines of describing a pipeline. I built a full-blown ML pipeline, and I could even automate it as part of the Git workflow. There's actually a pretty cool demo repository. We've done a joint webinar with GitHub and Microsoft on that, is how to build a fully automated CI/CD pipeline. So you can use that actually project It's using some CI tool called GitHub Actions, the GitHub CI tool. And essentially, I can post the code into my Git repository. And in the pull request, I can just tell it, go and test my code, test my pipeline. It will automatically create a machine learning pipeline to test my entire code, respond back into the repository, into the Git repository with all the scoring and all the analysis of my model. And that could also be used as a way to audit the progress or collaborate between different people. You know, one guy is doing a change at the model, running it, you see the results. The other guy with the elevated permissions say, you know what, /deploy, go and deploy that model to a beta cluster or production cluster. So this allows you to build it in a more collaborative manner, an automated manner. And by the way, it has a nice widget that goes into Slack. You can, you know, when it finishes the CI, it essentially throws a nice Slack widget with the results of each step. So you don't even need to wait for that. So that's again looking into that pipeline. Not this one, sorry. You know, here this is more of a like a beefy cluster. You can see this is the training job that I used, HyperParam or AutoML. You can see that MLRun records all the different experiments and chooses the best one with the best accuracy in this case. Okay, any questions until now? There was a question, does Nuclio and MLRun also handle training? This is exactly what I showed here. That now again, there are many other examples in the demo repository. One of the nice one is distributed machine learning, deep learning. There is if you're familiar with the Horvath, which is essentially a distributed deep learning processing engine. So there is a nice demo of how you can essentially ingest images, do image preparation in a distributed fashion, run distributed deep learning training, and then distributed serving. So everything in that framework is always distributed. You just have a way to control the level of distribution and elasticity. There's actually going to be a webinar by one of our data scientists on how to use Dask and all these sort of best practices from working with Dask for quite a bit. And even if you go into to MLRun, you know, there are all sorts of examples, like how to do MLRun Spark operator, MLRun Dask operator. So essentially, you can actually run a Spark job as an MLRun job. It will automatically orchestrate the distributed Spark cluster for you. So again, it supports many different distributed processing engines, and again, all of them are sort of a breeze. Just going for a second into the Dask operator, you can see that the only thing I need to do, I can add into the function specification things that are runtime specific. Like in the case of a Dask operator, I can specify like the elasticity, you know, scheduling constraints, and other things like dashboard information. The same for Spark. So Spark will have things like the jars that you would need as an extra. Same for Horvath. You can also specify the number of GPUs that you want to have for every execution, all through the function specification object. Okay, so I hope that addressed the question. Yes, obviously it does training. It does. The pipeline that I just showed you guys was CI, data engineering, training, validation, and CI again deploying. So you would usually use, in order to run the same pipeline, you would use CI, you'll use something like Jenkins, and then you'll use data pipelines, like Apache Airflow, and then you'll use a machine learning pipeline like Kubeflow, and then again Jenkins for CI. What you've seen is a single pipeline that covers all the automation from the CI, you know, building the containers, running the data preparation tasks, doing the training jobs, deploying to production, and testing your deployment, all in a single pipeline. So like maximum automation you can achieve. There is a question, which async systems have you used? I'm not really sure what you mean by the question. Do you mean like streaming or in what notion of async? So as I mentioned, Nuclio supports about 13, 12, or 13 different streaming protocols. Most of our customers use Kafka. We have some customers using Kinesis. We have customers using RabbitMQ. In Azure, some use Event Hub. In Google, there is PubSub. So we support all of those. And also there is, MLRun also supports scheduling. When you do jobs, beyond just, you can create jobs from function, as I mentioned before. So then essentially the function that I created on the notebook becomes a managed function that those parameters that I document in the notebook could be used later to launch a job, and I can even use scheduled jobs. So again, cron or just simple jobs. So everything could also be asynchronous and real time. Okay, I hope it addressed the question. So we were talking about that part. Again, there are many other demos that I can show you. There's a pretty cool demo of real-time stock analysis, which is essentially reading data from Yahoo Market, doing NLP analysis. Let me show you the slide on that. So there is a demo that shows how to read the data directly from a reference run training using MLRun. Store the model in the model repository of MLRun. And then you essentially have a set of Nuclio functions that are doing real-time scraping from Yahoo public data, running it against a BERT model for NLP processing, throwing all the data into the feature store, and then have other microservices, real-time and batch, that do analysis of that data using several analytics engine. So there's also a demo, it's called demo stocks, that you can go and deploy this entire thing. Just think about how much effort there is in deploying such a thing into production. That using that framework, hopefully a managed service or building it yourself as a managed service is a matter of days to build this entire pipeline. Okay, let's look into a few other points that we talked about. So feature store is part of MLRun. I'll show you a quick demo of the feature store. It's not fully announced yet, but it's cool because I see that people keep on asking about it. So why do we really need a feature store? Okay, and what is a feature store? So think about the traditional work of you have like a data engineering pipeline in Hadoop that takes data off a data lake and creates sort of curated data in an offline store, like a Parquet file or a data warehouse. And then you run training. Usually the MLOps and data science is in Kubernetes, and sort of the data engineering is in sort of Hadoop. And then comes the production pipelines. Production pipelines is not coming off a data lake. You actually have real data flowing from your Oracle, Teradata, streaming data, logs from web services, APIs that reports additional data. And then you essentially have to process that using streaming technologies and place it in an online store, which is randomly accessed, like a key value or a SQL database. And then you have the model serving function and model monitoring. Model monitoring has to respond back, with all the information goes back into the pipe and goes again and again. So this is really complicated because you have 4 disciplines to manage. So the trend in the industry is to move into a concept of a feature store, which means that instead of having 2 separate pipelines, have one pipeline. Maybe internally it has different processing engines used in order to form the pipeline, but essentially you define it once, you work with it once, and it knows how to store data sometimes in multiple layouts. In Iguazio, we have an advantage of a processing data engine that does random and sequential. So for us, it's a single engine, but in many cases, people will use like a Cassandra and Parquet or data warehouse, okay, to store those. But logically, think of it as one component that gets data, stores it in multiple forms, and allows the training jobs or the serving jobs to work against that data. And you may even build other applications off of that, maybe a dashboard or some triggers. Maybe the models doesn't want to go and get the features. Maybe you need to push the features into the model as a stream. So that's one thing. Another important aspect is that as we're going into auditability, monitoring, and all that, how do we monitor drift? The monitoring of the drift is based of analysis of the differences between training data and serving data. So if we have a feature store doesn't only store the features, it also stores the metadata and the statistics of the features. So feature store is also very essential on all the anomaly detection and outlier detection and validation of data schemas, and also the feature store is where you're putting back all the data from your serving functions back into the feature store and comparing it later with labeled data in order to identify accuracy problems. So again, feature store is a very important part of MLOps. There aren't many today. We're going to announce one very, very soon without disclosing dates. And I'll show you an example of that in a minute. So, but again, it's using all those same components because all the computation engine that we've talked about, the training, the serving, the data preparation components are there. It's just adding a nice fluff of abstraction on top of it. We also talked about how to drive projects into production. So the overall process, which is recommended, and not many organizations get into that level of sophistication. But again, this is sort of what our customers are seeking to, is think of it this way. You have a Git repository, and someone is building, I know data scientists are not always fond of Git, but you need to get trained on that in order to get sort of a good source of truth for the code and the metadata. So you create a branch from the Git. You do some local development and testing, as we've shown you before, using a notebook or your PyCharm. You convert your notebook into a function, again, one line of code in the example I showed you, and then test it on the cluster. Doesn't work, go back to square one, retest and fix, and go back again. At a certain point, we want to move from development to continuous integration, to CI. So again, we create a pull request into the branch, and then there are some automation tools like Blake or Flask or Flake or others that do static analysis of our code, look for grammar mistakes, look for package issues, etc., security scans. And if we find some problems, it goes again back into our laptop and fixing the problems and going this ritual again. If we did pass that, we don't want to run the pipeline at that stage, because if we have a typo or some code mistake, we don't want to waste a lot of computation resources for training. So only after we pass the static analysis and some of the CI process, we want to do a testing of the entire pipeline. As I showed you before, you run the entire pipeline, you generate a pull request, and you merge that pull request. At this point, they may run additional end-to-end system tests on that branch. After you've done the deployment, you can essentially create some tag or a branch out of that. You deploy canary, which means you take this model and deploy only portions of the traffic goes into it. Also, by the way, supported by Nuclio and MLRun, sort of A/B testing and all of that. And once it's passed, you just promote it to 100% of the traffic. And this is where you're starting to monitor your drift and activities, etc., to see that maybe you have to go back into training, etc. So this is how you do the development, the CI, the continuous integration, and finalize with the continuous deployment. Okay. So just before I open it to the Q&A, because you guys were so nice and asked about feature store so many times. Let me open sort of a feature store demo. I think I have it here. Okay, so let's assume that a financial use case. I have several data sets. I have the actual quotes from the transactions of the stock market. I have the trades. Now you see that they have timelines, but the timeline is not always aligned. They don't have to align because the bids and the prices are not modified at the same time. We'll use that to demonstrate the concept of time traveling. And then I may have another table, which is just sort of, for every ticker, there's another set of metadata. And so what we want to do is essentially create, go to the feature store, which is part of the future MLRun version. And then we want to create feature sets. Feature sets are a set of features that are usually produced together. So again, I'm creating a simple feature set of the stocks. I'm giving it the data frame from the stocks and telling it go in just that feature set. By the way, also analyze that feature set while you're ingesting it. So analyze the statistical behavior, analyze the schema, where you can think of it, and that analysis result is going to be used later in the pipeline where we're doing outlier detectors and drift detectors, etc. So again, I'm ingesting a simple data set, but in many cases, the data sets are not simple and they require a computation pipeline. So, you go now and play around with pipelines and Spark and all of that. Another option is to define the computation pipeline as part of your feature store and let the feature store deal with processing it in real time, in batch, and all the different variations. So I'm going to take the stock feature set, the stock quotes feature set, and I'm going to do a few manipulations on that. One is I want to do like apply some function, just creating some dummy columns on it. I want to apply aggregations. So I want to do like sum, max, standard deviation of certain time windows and periods on that data for 2 columns. And then I want to see what's going on if I'm going to run this pipeline before I'm running it in production in a real-time pipeline or in a batch on each data set. Let me try it out. So when I'm taking that feature set, I'm saying infer, it actually also simulates the production pipeline. And you can see it forms all those aggregation matrix, all those calculated matrix, etc. Now, what I've defined is a manifest of a feature set. I'm not really processing it. It records that all that definition, it will be able to run either in real time using Nuclio and a stream processing engine that Nuclio has, or in batch using MLRun jobs. But the definition of what I've done is exactly the same for both use cases. If I'm looking into the actual quote set, the actual feature set of the quotes, you can see that this object recorded all my schema types. It recorded all the different manipulations that I'm going to do on my features. It actually records where it's really stored in different, like in this case, in NoSQL database and on a Parquet file. It records all the statistical analysis of my data, which again is going to be used for other things. Okay, so this is all done automatically for me. Now, let's assume at a certain point I want to use that for training. So what I'm going to do is just say, this is a bunch of features I want. I want from the stock quotes, I want a bid, I want, some aggregation of the ask. I want, the ask, just rename it to a different name. And I want all the columns from the stocks data set. So essentially, I'm just saying, get me an offline feature set with those features. There's a notion of something called an entity row, which is what I'm going to join with and do the time travel based. Which column is the time column in the input stream, and I'm just going to generate a data frame. So you see, I didn't do any analytics, no Spark, no nothing. Maybe it's actually going to run Spark behind, but you don't need to care about it. You define the engineering pipeline, You define which features you want, and you're going to get your results and feed that result into the training engine. In the serving, it's actually quite different. I'm not going to use all the rows. I just, there's a user logging in. I want to create a feature vector for that user or that ticker in our case. So I need to create an online feature service, which means launch either a Nuclio or a real-time pipeline for processing that pipeline we talked about before. And once I have this pipeline ready, I can just give it, for example, a ticker or a set of tickers, and it will respond in real time. Within milliseconds, it will respond with the feature vector. So that's the difference that you asked before. The feature vector in training could take 15 minutes or more to calculate because it's joining and it's doing as of joins. It's doing time traveling on lots of data. So that can take a while. When you're doing the serving, you want it immediately. You want to give it a user and gets the feature vector, put it in against the model, and respond again. So that's again, you guys asked. I didn't prepare for it, but you can see how feature stores work. And by integrating a feature store with the same framework that have all the training framework, the model monitoring framework, now it's all glueless. If you're going to take a feature store that is not connected to like a training engine or connects to the model monitoring engine, you would need to build all the glue logic yourself, which is a lot of glue logic. Okay, let's see what other questions we have here. Yeah, so we mentioned feature store is going to be part of MLRun. What is the title of the study you mentioned? Have a bunch of titles, but I think what you can look into if you go into Medium towards data science, toward data science. And search my name, you'll find a lot of blogs that I've published. Okay, so they're talking about all those different things that I mentioned. There's actually one on Kubeflow from last week, from a few days ago. There's one on distributed GPUs, I think relating to another feature. There's another blog that one of our guys wrote about feature stores, also very popular, that Adi wrote. So again, and by the way, you can just link in to me and connect and ask for material or through Slack. There's MLOps live Slack that you can join into, and then there's a live discussion there on. If there is the bi-weekly webinars that we're running. Again, the next one is about. Let's see the webinar. There's lots of videos. There's a huge amount of following to those videos. I think tens of thousands of YouTube views on those. There's lectures from Netflix and from Spotify and Microsoft and NVIDIA and others. And there's the MLOps live webinar series, which is sort of a bi-weekly session. And part of it, it also has the integration with the Slack. I don't see the link. But again, ping me and we'll get you invited into the Slack. So you can follow up on that. There's a question here. I think Kubeflow abstracts that away from you. Write the function, it runs containers. So Kubeflow is still working. A lot of it, it's not really abstracted like here. Everything is a managed execution. You still need to write YAMLs. There is an SDK for running the YAML, for writing the YAML, so it's not always like pure YAML, but it's not really managed execution. The components don't necessarily fit in. You can read my blog, like there is hyperparameter project in Kubeflow called Katib, but it doesn't work with the pipelines in a seamless way. But you've seen here that when I want to run AutoML or hyperparameter, I just add an extra parameter to my execution. I don't need to integrate with a separate component. The serving engine in Kubeflow, again, Nuclio is one of them, but The others are not, again, tied into the pipeline. So this is one of the things that you'll find yourself using, and it's all detailed in my recent blog post that you'll need to work around. So you can take Kubeflow and you can take MLRun on top of it, which is also open source, and it solves many of those issues that I outlined. Okay, any more questions? See a question, why is serverless better than regular containers, way of deployment? So again, think, what is the building a container? You need to take your code, you need to create Docker files, you need to create scripts and CLI commands to inject data into your function. You need to build around it, monitoring, logging, telemetry. You need to build security execution roles, all those things. This is a lot of work. Think about just auto scaling. How do you auto scale? So now you need to put an API gateway and a load balancer in front of it, and canary deployments. Yet another thing. If you want to do Kafka streaming, how do you do checkpointing and consumer groups? And there's lots and lots of work that if you're fond of DevOps, that's okay. If you just want to get things done by leveraging something that just takes code and turns it into a managed execution engine, it's going to save you so much time. Okay. By the way, one of the things that we talked about was all this notion of API gateways and canaries. So if you want to add like an API gateway to a function, it's as easy as creating something and just creating another function, and you could dial the percentage of traffic that goes into each one of those, and even the authentication methods, a bunch of authentication methods that you can apply. So the container doesn't do all those things for you. You would need to go and do like service meshes and ingress gateways and API gateways and deploy canaries and all the policies around canaries and all of that. We talked about model monitoring, the same. So this is where usually what we see is that people underestimate the technical depth in building a true pipeline, and they end up spending like 12 months on a project and hiring a bunch of people and going over budget. And what we're trying to do with people is essentially shrink it into a matter of weeks with a lower budget on CapEx, because using elastic nature of containers and serverless function means that you're going to use less Amazon infrastructure, and also cutting costs because you're going to do a lot less work. So also operational costs are cutting down significantly. Yeah, so creating the API gateway is again part of the Nuclio engine. Currently, it's part of the commercial version, but I think in the last version it's also already moved into the open source version. So, there's also more sophisticated routing rules that are not supported in the UI. So again, ensembles, multi-arm bandit, all of that, they're supported as part of the Nuclio or MLRun serving engine, and there's some documentation around that. Multi-tenancy, yes, working. So our commercial solution works on premises. It's also co-sold with a bunch of partners like NetApp, NVIDIA, Dell, and others. We have a commercial solution in the customer VPC. Most enterprises prefer it this way. They have an Amazon or Azure or Google account. They build all this managed service in their VPC, and there's a managed SaaS service that anyone can just log in and use it. So very strong security throughout the system on data, on APIs, on secret store, and all of that. And again, fully operationalized, fully commercial solution. The question, there's multi-tenant. Again, you can pick me on offline. I'll explain the different levels of how multi-tenancy works, and using VMs or a combination of Kubernetes namespaces and VMs. And so, thanks for all the good feedback. and you've been a wonderful crowd. Lots of questions. So it's fun to have an interactive session. Again, don't hesitate to contact me offline or online, and I would love to have. We have a great team of data scientists. They're involved in lots of projects and very operational ones. So they've learned a lot of best practices that even regardless if you're our customer or not, we'd love to help people move to more operational work in that space. So the Slack. You know what? If people will stay for a second, I'll just create a Slack link that people can just join into. So I created a Slack link for MLOps Live, so people can join. There's a lot of people there from different companies that sort of share knowledge, blogs, exchange thoughts. And this is also where we make announcements on the different MLOps Live series webinars. Again, the next webinar is going to be about using Dask at scale, different technologies, Dask, Vax, Spark, and how they compare, and with one of our data scientists. Okay, good. So thanks everyone again, and was fun chatting with you. Bye.